Welcome to another unit in this workbook statistics. This time I'm going to talk about linear regression, and in particular in this case about the method of least squares, how we can use it to determine the coefficients of a regression line, and how we can use the coefficient of determination to assess the quality of our regression. The general idea behind a linear regression is that we take our data points, the dependent variable y and the independent variable or variables x, and we try to fit a function, in particular if it's about linear regression, a linear function to this so-called cloud of points, so the set of data points we have here. Whereas we want to fit this function in a way that the distance, the differences, are as small as possible. So the line should be the best fit for the available data. Well, in this case, before I talk a little bit about how we actually proceed in doing this, in this case we have to adhere to some general underlying assumptions for this to work out in a decent fashion. First one, we assume that only x impacts y but not the other way around. So we do not have any kind of feedback relations, and we already have to ascertain which of the variables are dependent, which are independent, before starting with the regression analysis. We also assume that all variables are exogenously given and not stochastic, so we do not have random variables in our model. We have fixed values, fixed data points. We also assume that all the independent variables are uncorrelated, especially with the errors, with the residuals. This also means that they are uncorrelated with each other, which might be a bit of a big problem called multi-collinearity. Furthermore, we assume for the residuals, which are just the error in our estimation, the part we cannot explain with the line, that's more or less the distance of the line and between the line we estimated, we fitted, and our data points, that those residuals are normally distributed with a mean of 0. So on the one hand, if we take the average of the residuals, we get 0. On the other hand, they're also following a normal distribution pattern. Then we also assume that they have a constant variance. So for example, smaller values have the same spread as larger values. So if it's not this case, we call this as well heteroscedasticity, meaning, for example, in some parts of this cloud of data points, there's a larger spread, in other parts there's a smaller spread. Well, we do not want this, and we also do not want the residuals to be pairwise correlated, so we do not want to have any kind of underlying structure as with autocorrelation. Once all of these aspects are fulfilled, we can actually start with the next approach. I'm going to propose to actually realize this goal, which is written down up here. The idea, first off, summarized graphically, we have this point of, or this cloud of data points with x and y coordinates. As I said, I'm going to start really simple with just one x, one y variable. We're going to fit a line in this way so that the distance between points and line on average gets as small as possible. How are we going to do this? Well, first off, we're going to consider the distance between line and point. Whereas those are given, this line at the moment is not yet fixed. So we use an arbitrary line, or rather a line with arbitrary coefficients. Well, if we use the distances, we might have a big problem. Here we have positive distance, here we have a negative distance. So they might cancel each other out. So how to fix this in the most easiest way? We're going to use the squared distances. That's the same idea we follow when calculating the variance as well. So we take the squared distance, we calculate the squared distance for all data points. We're going to add all these data points up in the next step, then we're going to minimize the overall area of these squares. Well, how can we actually calculate the area of these well, squares. First off, we have the y value of our data point. That's given already. However, we can also calculate this y hat value. That's the value we get if we insert the original x coordinate into our artificial line. That's the y value of the line at the same coordinate as this point for x. So we get y hat, and this gives us the distance here. Now we can simply square this, giving us the area of this square. Our goal then, well, take the sum of all the squared differences and minimize this. That's what we're going to do next. Actually calculating the sum of the squared differences for all of our data points and then minimizing this sum. Mathematically, this is called the method of least squares. So we're going to take the difference, as I said, between the actual values and the values we get from our line. We square these differences and we sum this up. So we're doing this for all observations, and then we're going to add up the area of all the squares. The advantage is we could replace this y hat in an easy way by simply using an arbitrary formula for a regression line, for a linear function. Linear function has a as the intercept and b as the slope. Well, that's more or less how we could write the information we have. And then our task was find the line in a way that this expression becomes as small as possible. So what we are actually asking for is the minimum for this expression based on a and b. So we're simply going to calculate a minimum of a function with two variables, with the variables a and b. Well, if we calculate a minimum of a function with two variables, we need to derive them for the first and the second variable. After expanding this, that's actually what we're going to do here. We calculate the derivative regarding b, regarding a, in both cases. Well, we have the derivatives, so the next step would be we equalize them with 0 and then solve for a and b. Well, solving for a and b, the first part would actually be getting rid of those pluses, so we're going to expand this. And we see there's 2, 2, 2 here as well, so we divide by 2. This makes our life a bit easier because in this case, the a and the b are fixed, so we can pull them in front of the sums. And, well, this part here doesn't have any x or y at all. So this is fixed. This is already easily calculated as minus a n. So we can use this and then reformulate these two equations. Particularly for the first part, for the second equation, we can divide it by n and then bring the remaining part a to the other side. So in other words, once we know b, we can easily calculate a. That's one interesting thing, but also these sums look really familiar because this is nothing else than the average of y. This is the average of x. Well, we can already calculate those two, so we only need b, and then we can calculate a. So this simplifies to this expression down here, so we just need to find out how can we get to b. For this, we're going to use the other equation. We're going to divide this by n as well. And we could replace the a with what we just determined up here. So we only are left with one equation, one variable, the b here, the b here. Then we're just going to solve this for this parameter b. So we factor out, solve this for b, we get this result here. Well, this is a bit of a large formula, but we can write this in a much easier way. Because this part in front is nothing else than the average of x times y. Here we have average of y times average of x. Down here, this is nothing else than the average of x squared. This is just the average of x to the power of 2. So this gives us b. This formula, or rather that formula, gives us a. So we calculated a and b in a way that if we set them like this, we will get the respective line which minimizes this average squared distances of the line from all the data points. So that's actually the best solution we could come up with. And this already was the so-called method of least squares. So if we summarize this, that's the two formulas we have to use. The problem, however, is we do not yet know how good this line actually is, how good this line actually fits. We know it's the best one, but the best one could still be relatively bad. So what we do next is talk about the so-called coefficient of determination. This one tells us how good is our relation actually. So again, if we have our data points, we put a line through the data points. That's what we actually did, determine this line. Then we can also, in this graph, put the average of all y's. Not like, it's like if we do not know anything, the best guess about a y would be the average of all other y's. So this is our reference baseline without any information. So if we consider this data point, that's actually, if we do not know anything, how much we would have to guess, how much we would be off. So that's the total variance, so to speak, of y, because variance is nothing else than the distance of a data point from its average, and then the whole thing squared. But at this point, we do not actually have all this which we cannot explain, because our regression line already shortened the part which we cannot explain to this small area up here. So we can explain quite a lot of the actual variance by simply using the value from our regression line. And that's what the coefficient of determination is all about. Which share of the total variance of our y could we explain if we use the determined regression line as well, a measure, as a helpful tool, and not refer simply to the arithmetic mean of the dependent variable. That's why we could add some additional notations here, which would make this formula even more understandable, but in general it's the same idea. The coefficient determination, also called the R squared, is just the explained variance of y divided by its total variance. So it's rather the share of the variance of y which we can explain if we use our regression model. Mathematically speaking, well, the part down here is the variance. That's the distance between those two values squared. This up here is the explained variance. That's this value minus that one squared. Well, I would have a 1 divided by n here and here, but they cancel each other out. So we do not need them. We could just simply write down these sums. So that's the main idea behind the coefficient of determination. That's also the basic formula to calculate this. So here I'm just repeating it. We could also then, well, as I said, see this as some kind of variances, or, and that's the big advantage, if we have only a simple linear regression, we could make our lives even more easier, because in this case, R squared is nothing else than the Bravais-Pearson correlation coefficient squared. That's why here we also use an R, but just a big R. So with one independent variable, R squared is actually small r squared, so the correlation coefficient squared. If we have more than one independent variable, then we actually have to use this formula. Well, so much for the calculation. What else do we know about R squared? Well, it's the share of the variance we can explain. So this means that it needs to be somewhere between 0, we cannot explain anything at all, or 1, which means 100%, we can explain this perfectly. Our regression line exactly fits our observations. And well, as I said, the coefficient of determination is actually the share of the total variance that is explained via the regression line, or in other words, via the implemented independent variables. And well, that's then everything there is on our least squares method, on how to calculate the coefficients, especially for a simple linear regression, and how to calculate the coefficient of determination in a simple linear case and in a general linear regression case. Well, that's it. So I hope you enjoyed this session. I say goodbye and see you next time.